Hi, this is Dr. Han. Today's lecture is about Chapter 8. Okay, this is Prepare for the MA 3333 Systems and Vibrations. So, Chapter 8 is about free response. Free responses of a first order system and a second order system. Yeah? And for this lecture, I'll be covering 8.1 and 8.2. And the next lecture will cover 8.3 and 8.4. So going to the first order system. Okay, so this is a system. Okay, this is a system model that's obtained for a mass. Okay, for a mass with a damper. Okay, where the damping coefficient is given by C. Okay, so here you have an external force of F of t and a coordinate x of t. Okay, so when you draw the free body diagram, you still have external force. Okay, since the position is defined positive to the right, the velocity is also defined positive to the right. Okay, that means damping force will be in the direction opposing that. So this will be C times V. C times V. Let me give it a little more space. Okay. And so when you sum the forces equal to MA, you'll get F of t to the right. So you have to sum the forces also in the same direction as acceleration, which is defined positive in the same direction as x. And minus CV equals MA. Okay? So where we do know the velocity is x dot, where and acceleration is x double dot. And we can rewrite this and switching after switching signs and replacing A with the V dot. Okay, we have the first order system. Okay, so now we're only considering the free response. So that means we're going to set the right hand side equals to 0. We're going to solve this with the initial condition. Okay, so the characteristic equation is given by M times R plus C equals to 0. So if you don't recall how to find the characteristic equation, you need to go back to chapter 2. And R is negative C over M. Okay? So that means you have a V, the homogeneous solution, equals, you have some constant, okay, times e to the minus C over M t. Okay? And after applying the initial condition, at time is equal to 0, you have an A. You realize A is the initial condition for V. Yeah, so that's how we find this free response right there. Okay, I just drive that equation. So the time constant tau has many different names. Okay, time constant, that's just the one name for the time, that tau. And another name is what's called the characteristic time or relaxation time. Okay, and it's only applicable for exponentially decaying function. So if you don't have an exponentially decaying function, you just forget about finding the time constant. So what is a time constant? Time constant is time it takes, okay, for the exponentially decaying function to decay to e to the negative 1 of its original value. Okay, can you write that in terms of equation? So at time is equal to tau, what happens? You have a V 0, I'm just plugging in e to the minus C over M times tau is what? E to the negative 1 of the original value. Okay, e to the negative 1 is a number. This is 0.3679 or 36.8 or 37%. Okay, so this is the time it takes for an exponentially decaying function to to decay to 37%, will lose 63% of the original value. Okay. So in our case, when you look at this, when does this become -1? So time constant is now m over c. Okay. So it wouldn't make any sense to give me a negative number. If I ask how long does it take, such and such, then you better give me some positive number, right? You're not going to give me any negative number. So sometimes people love formulas, and sometimes they miss the sign of the formula, and sometimes they just give me some negative time, and it doesn't make any sense. Well, the answer is supposed to be 3 seconds, and people give me -3 seconds. It's automatically a wrong answer. So let's try this. Is this an exponentially decaying function? Yeah, it is. Okay, has time constant of what? What is tau? 3 seconds. Okay, 3 seconds. I'm assuming t has a unit of second. Okay, for example, on that example, if I have e to the -2t, has a time constant of 1/2 second. Okay, or 0.5 second. Okay, so what if I say e to the 2t? Okay, then you should say immediately nonsense. Okay, don't ask me those questions. It's not an exponentially decaying function. So there's only one. Okay, there's only one parameter that for a first order system. So if you remember from chapter 2, recall chapter 2, the first order system, okay, was always written this way. The standard form for the first order system was tau times x dot plus x. Okay, only the homogeneous equation only, please, equals 0. Okay, so where tau was automatically what? Time constant. Okay, so now let's go to 8.2. So 8.2 is about the same. It's about the second order system. So where did I get that equation? So this is from, yeah, this is from a mass, spring, and a damper system. Okay, this is C, where K is a spring constant, and X, let's define X this way. And then here, I just got rid of the external force. Why? Because I'm only going to be considering the free response, the homogeneous solution only. So let's try. So the free body diagram will look like this. You have to assume positive displacement. So that means spring has to pull back by K times X. Same thing for the C. It has to exert force that's proportional to the velocity, okay, in the opposite direction of the positive velocity. So when you sum the forces, it goes to 0. MA. Okay, MA. Make sure you sum the forces to the right, and you're gonna have minus CX dot minus KX equals MX double dot. So you have MX double dot plus CX dot plus KX equals 0. So that's an equation of motion for a second order system. So depending on the values of MCK, you can have many different kinds of roots. But you know one thing for sure, you'll have 2 roots, right? Maximum of 2 roots. In fact, you'll have exactly 2 roots. So if MCK of the same sign, okay, the characteristic roots are on the left-hand side, and the system is asymptotically stable. Okay? So in chapter 2, what did I say this was? This was a statement for the Routh stability criterion. Yeah, but not the whole thing. The actual Routh stability criterion is actually very, it applies for a higher order polynomial. Okay? So for the second order, it's actually not that difficult to show that this is true. So let's see. We have a characteristic root. You have a characteristic equation given by mr squared plus cr plus k equals 0. So we're using the quadratic equation. What is r? Minus, how did it go? Minus b plus minus square root of b squared minus 4ac. That one. Okay? So you have a c. What is this? Okay. Yeah. Minus c plus minus c squared minus 4mk. The whole thing divided by 2m. Okay? So when you examine this carefully, you'll notice that this is always a negative number. If MC and K are all positive, this R, it's always going to be either negative in real, or it has, even if the square root underneath the square root is negative number, you'll have a complex root with a negative real part. Yeah. So you can divide this into 3 cases. Yeah. So case number one. So if c squared, this is called what's called the overdamped case. And this is a case when c squared minus 4mk is greater than 0. Yeah? So then your r becomes minus c plus square root of c squared minus 4mk divided by 2m. Or you have another root, minus c squared minus 4mk divided by 2m. True? Okay, so since c squared minus 4mk is a positive number, square root of positive number, it's a real number. Yeah? And you can see this is a negative number. It's not hard to see that this is a negative number. Okay, and real. Okay, and can you see that this is also negative and real? I mean, you can plug in some numbers, make sure MCK, they're all positive. Okay, all negative, whichever. Okay, they all have to have the same sign. So I can tell that if I compare the two numbers, c and square root of c squared minus 4mk, which is a bigger number? This one, right? Okay, c is a bigger number than c squared minus 4mk. So now you can tell when you have a negative c plus a smaller number than c, you get a negative number. So I can tell this is also negative and real. Okay. So for example, if you have something like x double dot plus, let me see how is something that I can factor, 3x dot plus 2x equals 0. You have a characteristic root equation that's given by r squared plus 3r plus 2 equals 0. You have a r plus 1, r plus 2 equals 0. And r is negative 1 and negative 2. You have x of t is given by, so this is just a homogeneous solution. So what's the difference between homogeneous solution and the free response? Same thing, right? Homogeneous solution will have unknown constants. Constants are not substituted, not evaluated. With the free response, we'll have the C1 and C2 evaluated. So let's see, C1 e to the minus t plus C2 times e to the minus 2t. So what does the response look like? You have time t, you can have x free sub t, so it may look like this. Okay. Hang on. Let me make it exponentially decaying function. Okay, how about this? Is this good? Okay. Okay, so next. So this was the overdamped case. So remember, okay? Overdamped means you have two negative real roots. Okay. And then you have where both functions are exponential decaying function. So let's see. So let's go to case number 2. Case number 2 is what's called a critically damped response. or system. So that's when you have c squared minus 4mk equals 0. Okay, so that means your roots will become minus c over 2m. And repeat it one more time. Yeah. So what does the response look like? X, the homogeneous solution will be some constant times e to the minus c over 2m t plus some other constant times t times e to the minus c over 2m t. Okay? So if you use L'Hopital's rule, you can find out the polynomial t times exponential decaying function will decay with time. Okay? So it looks like you might not know because t is increasing function with respect to time, and e to negative t is decreasing function. But when you multiply the two, exponential decay will win. Okay, win the race. So this will be a decaying function too. Okay, so it may look like this, where it also exponentially decays. Okay, so this is the critically damped system. So if you look at the response only, okay, if you look at the free response only, so this is your X free. Sometimes it's hard to tell. Okay, in fact, I'll say 100% of the time I can't tell whether it's critically damped or the what's the other one? Over damped. So now let's go to case 3. Okay, case 3. Yeah, so this is the what's called under damped system. Okay, under damped system. So this is the case when the c squared minus 4mk is now less than 0. Okay, so now the roots become minus c plus minus. Yeah, so now we know that c squared, what's inside the square root is a negative number. So what we're going to do is we're actually going to just take out the negative 1. Okay, we're going to do square root of. We're going to take a negative 1 out because I know it's a negative number. I know 4mk is greater than c squared. So we're going to write down 4mk minus c squared. So if you're wondering about what I just did, yeah, what I just did, I just rewrote c squared minus 4mk equals minus c squared plus, what did I do? Minus 4mk. I just took out the negative and I rewrote it as 4mk minus c squared. It's just a negative of each other. If you just switch the order, just negative of each other. So we write this as minus c over 2m plus minus. You're going to get 1 over 2m times square root of 4mk minus c squared, and you'll have an I in front of it. Yeah? So your response, do you remember what the response should look like? Your homogeneous solution will look like e to the minus c over 2m t, okay, times, now, can I use C1 times sine square root of 4mk minus c squared, okay, the complex number, okay, I meant the imaginary number, okay, imaginary part of the root, which is this, times t plus c2 times cosine of the same value, 4mk minus c squared over 2m times t. Yeah. So your free response will look like something like this, where it will be oscillating. Okay, we'll be oscillating, but we'll have an exponential decay envelope. Okay, and then this decay envelope will be proportional to, this is proportional to sine e to the minus c over 2m t. So it will be some constant times e to the minus c over 2m t. Okay, so this is called the envelope function. So this is called the envelope function. Okay. So now let's see. So in all three cases, what are the roots? Okay, on the complex plane. Okay. So for the first one, if I call this one the real part of characteristic root, and this is the imaginary part of the characteristic root, you'll have them somewhere like this. Okay. For the second case, when it's critically damped, same thing, the real part of R, imaginary part of R. Okay. Same place, but they're both negative. Okay, so this is at negative C over 2m. Okay. So by the way, characteristic roots are really plotted with x's, okay, on the complex plane. For the case 3, this is real, imaginary, and will be something like that. Okay, so the roots, they appear in pairs, right? You have complex conjugate pairs, so they have the same real part, but what? Imaginary part has different signs, right? Okay. So what did we say in the beginning? We said we'll have a asymptotically stable system, meaning all your characteristic roots will appear on the left-hand side, left F plane, and then we just showed, okay, for 3 cases, okay, for the overdamped system, critically damped system, and underdamped system, the roots all appear on the left half plane. Okay, and then you have to keep in mind whether they're overdamped, critically damped, and underdamped. They're all damped. Okay, meaning they all die. Okay, as the time goes to infinity, they're all going to disappear. They're all asymptotically stable systems. So let's see. Let's do an example. Okay, so you're supposed to tell me what kind of system you have. So if I do x double dot plus 2x dot plus 3, okay, x equals e to the t, what kind of system do you have? Well, you still have asymptotically stable system. Why? Because stability is determined. It's a system stability. I'm not talking about the response. Okay, so just look at the left hand side, ignore the right hand side. This is still the system itself. Okay, is asymptotically stable system. Okay, and what are the roots? You'll find that 2r plus 3, that's your characteristic equation, and you'll find that your characteristic roots are -1 plus minus square root of 2i. Okay, square root of 2i, or I times square root of 2. So what is this? Is this underdamped, overdamped, or critically damped? I mean, there's no question it's a asymptotically stable system, but right, your root is at -1 comma square root of 2 right here. So this is the imaginary part of R. This is your real part of R. Okay, where's the other root? Right here at negative square root of 2. 1 comma, -1 comma, negative square root of 2. Yeah, these are your 2 roots. Yeah, characteristic roots. So this is underdamped system. Okay, so this is an underdamped system. So now let's move on to it's not non-dimensional equation, it's what's called the normalized equation. Okay, so what do? We divide the equation by m. Okay, why do we do that? Well, instead of considering m, c, k separately, now we can manipulate c over m or k over m to get a response, right? So as long as the ratio of c over m, c to m, or the k to m, if they're equal, what I mean is, if you have a system x double dot plus, let's say, 2x dot plus 3x equals to 0, or let's double everything again, 2x double dot plus 4x dot plus 6x equals to 0, they will have the same, okay, homogeneous solution. Okay, so we just divide by m. Okay, so that we just have to consider 2 parameters, which are c over m and k over m. And we do something even more complicated. What we do is we let c over m to be same as 2 times zeta times omega n. And k over m, we call the k over m to be omega n squared. So we can kind of understand what omega n squared is. So omega n squared, that's your natural frequency squared. By the way, it's actually angular frequency, but we're not going to say angular. Yeah, whenever we say frequency, automatically it's in radians per second. So this is the frequency that you would have had if there's no damping. Does it make sense? Right? So if you have a system where you have x double dot plus 4x, this is x, equals to 0, what kind of solution do you have? That's equal to some constant 1 times sine 2t plus c2 times cosine 2t. Yeah? So you have a frequency of 2 radians per second. It oscillates at omega is equal to 2 radians per second. And what's the frequency in hertz? F is equal to F is omega divided by 2 pi. So that means you have 2 divided by 2 pi hertz. What is that? What's 1 divided by 3.14? About 0.3? Yeah, 0.3 cycle per second. And what is the period? Period is the inverse of that, right? So 2, let's cancel 2. You have a pi seconds. Okay, so let me put the units in the brackets. Okay. So you might be familiar with the hertz, but in reality, omega, radians per second, frequency, and angular frequency is actually much easier to deal with. Why? Because you can see them. Okay, whenever we have a sine 2t, what's its frequency? 2 radians per second. Okay, you don't have to do anything complicated like, oh, it has a period of 2 pi over 2, that's pi seconds, and then invert it to get a 1 over pi hertz, and then change to radians per second. You don't have to do that anymore. Okay, omega is just the coefficient of t right there. So those are your omegas. Okay, those are your omega n. In fact, it's called the natural frequency of the system. So that kind of makes sense. Okay, so this one, the name for k over m is the natural frequency squared. That makes perfect sense. What's the relationship between this 2 and 4? Right? How did I get this 2? This one was that 2 radians per second was the square root of that number. So now the next one is a little bit tougher. So next one is the middle one, c over m. Let's let c over m to be. Okay, let me actually write these down. Okay, there's 2 zeta omega n. Okay, let's let the c over m to be 2 times zeta times omega n. There's actually a perfectly good reason for it. Okay, and I think it's on the next slide. So before we move on, I'm gonna actually have to tell you the zeta. Okay, this is the Greek letter zeta. Okay, zeta is called the damping ratio, and then it's a ratio. It's unitless. Okay, unitless. Okay. Yeah. So why is zeta important? Why don't we just leave it as a c over m? It's because the zeta tells you the amount of damping you have in the system. If the zeta is 1, you say you have if zeta equal to 1, you'll have a critically damped system. If zeta is less than 1, you have an underdamped system. If zeta is greater than 1, you have an overdamped system. Yeah, why? The reason is in the next slide. So let's see. So it's actually easier than you think. So if you change, the characteristic equation in terms of omega n and zeta, so remember omega n, that one, omega n squared was what? K over m. And what was the middle coefficient? This one? That one was a c over m. Okay? Ooh, let's try to erase that. Okay. So now what's the characteristic root? If you use the quadratic equation. So how does it go? Quadratic equation. Let's see. R equals, b minus 2 zeta omega n minus b plus minus square root of 2 zeta omega n square minus 4 m k, 4ac, and divide by 2. Okay? So if you simplify this, you'll get zeta minus zeta omega n plus minus omega n will come out of the square root sign, and you'll have a zeta squared minus 1. Okay, so this expression is perfectly fine for overdamped system. Okay, but for underdamped system, this, see, you see the number right there inside of our square root. For the underdamped system, that number is less than 0. It's a negative number. Okay, so for the underdamped system, we're gonna just take the negative 1 outside and call it. We take the negative square root of negative 1 out, so we get plus minus I, the imaginary number I, times omega n times square root of 1 minus zeta squared. Okay, so you can see from this expression, if zeta square minus 1 is greater than 0, which means that zeta is greater than 1. Zeta, by the way, is a positive number, right? Because we're assuming MCK, they're all positive numbers. Then we have overdamped system. And if zeta squared minus 1 equals 0, that means that zeta equals 1. I'm dropping the negative 1. Why? Because we already assume MCK all positive, or the same root, the same sign. So now you have a critically damped system. In the last case, you ready? If zeta squared minus 1 is less than 0, that means that zeta less than 1, you have underdamped system. Okay, so just looking at zeta, we can tell right away whether it's overdamped, underdamped, or critically damped, which we cannot do by looking at C or C over M. Okay, we have to actually find the roots, right, when you're given MC and K. So now one more. Okay, there's one more in the slide. So when you have underdamped system, we're gonna call this omega n times square root of 1 minus zeta squared. That's the frequency, right? Okay, we're gonna call that omega d. So that's called the damped natural frequency. So should I highlight it? Let me highlight this. Okay, it's damped natural frequency. And so unfortunately, it's one of those things you're gonna have to memorize. But since our test is gonna be take home for this semester, meaning 2020, spring of 2020, yeah. Then I suppose you can have a cheat sheet. Okay, for any other semesters, you'll have to memorize it. So let's see. So this is continued from last slide. So for the underdamped second order system, you have a free response that looks like this, where you have an exponential decaying function times sine and cosine. Okay, so another way to write it is to write it in terms of in the amplitude and the phase form. Yeah, amplitude and the phase form. So you can rewrite A times cosine omega dt plus B times sine omega dt, okay, equals C times sine omega dt plus phi. How do you do that? Okay, why don't I just do one right now? Okay, so let's say you have, how is the A and B determined? Initial conditions, right? They're determined by initial conditions. So the trick is you rewrite the right hand side using the sum formula. You have a C times sine omega dt times sine, cosine phi plus C times sine cosine and sine phi. Okay. So what you do is now you match the coefficient. You can see cosine omega d, cosine omega d right there, cosine, sine right there, you match the coefficients. So you have A must be equal to what? C sine phi, and you have B equals C times cosine phi. Okay? So given A and B, you solve for C and phi. Okay? I'm sure there's a formula for this. Okay? There's a formula somewhere, but it's a little hard to use. Why? Because if the formula is given in terms of arctangent has two values, right? For the angle, for the argument between 0 and 360 degrees. So should I really do one? Yeah, why not? Okay, let's say you have, I'm going to give you, let's see, how about I give you third quadrant, okay, phi. So that means if it's third quadrant, all students take calculus. Should be negative. Okay, both negative. Okay, I got it. Okay, so let's say A is -1, B is -2. Okay, and if I say find C and phi, okay, so you have something like this is equal to C times sine. So this is an example. Okay, example. I made up those numbers. Sine phi, C times cosine phi. True? Okay, so how to find C and phi? One way to do it is okay, this is equation 1, this is equation 2. Why don't I just do 1 square plus 2 square? Okay, so you should get C square times sine square plus cosine square, which is 1. Okay, which is 1 sine phi cosine phi square. That's the right hand side. That's equal to 1 square, -1 square plus -2 square. That's 5. Okay, so that means your C is either positive square root of 5 or negative square root of 5. So typically we actually take the positive value. Okay, so typically if you take the C is equal to, let's just say, okay, let's say this C is equal to square root of 5. Okay, so now you go back to it. Okay, we do know what C is. How do you find the phi? So typically what people do is you divide. Okay, let me get rid of this. Yeah, you divide those two equations. 1 divided by 2. So you get tangent phi equals 1/2. 1/2. So here's the problem. You have tangent phi that's equal to -1 divided by -2, but signs are lost. Okay? So if you recall, tangent phi equals, what is it? Y over x, right? Y over x, right? So you have -1 and -2. So when is y negative and when is on what quadrant is y negative and x negative? Third quadrant, right? Okay. But if you just use a calculator, what would the calculator say? Well, whatever it is, it's a wrong answer. So let me see. I have MATLAB open on the next window, so I'm gonna actually do it. So I'm gonna do arctangent d 1/2. Oh, I want to memorize this number. That's 26.6 degrees. So this is 26.6 degrees, which is wrong. Okay, you have to find one in the third quadrant. So this is wrong. What's the other answer? Tangent is positive in the third quadrant, right? So you have to add 180 to it. So 180 plus answer, I guess. Answer. Okay, so the 206.6 degrees. So 206.6 degrees. Okay, in fact, it would be better if you use radians. We should use radians. We must use the radians actually. Okay, let me say answer divided by 180 times pi. What is this? It's 3.61. Okay. So we find this is equal to 3.605 radians. Okay, so I have an answer right here. Okay, so if I have -1 times, what am I, cosine omega dt plus minus 2 sine omega dt. This can be written as square root of 5. Okay, square root of 5 times, did I do sine? Yes, sine omega dt, okay, plus 3.605 radians. Okay, the reason why it has been radians instead of degree is because omega dt is in radians. Omega d is always in radians per second, and t is in second, so that's in radians. So you have to write radians, right? It wouldn't make any sense to write 20 degrees plus like 5 radians, right? Okay, you want to match the units. So now, okay, well, by the way, this used to be on the test all the time, but I think I realized that's pre-calculus. Okay, so this is actually a summary of what we talked about. If you have a characteristic root, okay, that's complex, you will have oscillation, right? How fast the oscillation dies has to do with the real part. Okay, so this real part controls how fast it decays, right? This one decays a lot faster. Why? Because B is to the left of A. Okay, you see that? The root's right there, right here. Okay, further to the left, we call it, you have a faster, okay, what's called the fast poles, meaning the fast characteristic root. It's hard to say characteristic root, so we say poles, same thing. Okay, if you don't have any the real part, right? If your characteristic root is just the j omega, what was it? You have a neutrally stable system, right? Okay, neutrally stable system. What if your real part is positive number? So that's right there, that one. Then you have unstable system. So do you recall this, the rules, stability rules? So this is the real part, this is the imaginary part. Okay, so this is unstable. Okay, this is called the right half plane, this is called the left half plane, this is called the imaginary axis. Ooh, why is everything so thick? Okay, let me switch over to blue. Yeah. Oh, okay, here it is. Okay, so on any poles on the right half plane, you'll have unstable system. Look at this. Okay, if you have complex part, if you have imaginary part, it will oscillate while you're increasing, right? Blowing up, right? Yeah. How about here? How about right here? Same thing, right? It will just blow up, right? Okay. What is free responses? So now the left half plane, what was the rule? This was asymptotically stable. And then this will what? The response will always decay to zero. Okay, decay to zero. Okay, decay to zero. Yeah. So if you're on the imaginary axis, okay, two cases. Okay, if it's distinct, meaning it's not repeated, right? Okay, then neutrally stable. Okay, if it's repeated, was unstable. Okay, unstable. Okay, so this graph is just supposed to tell you all of that. On top of it, for the left half plane, for the asymptotically stable system, depending on the values of the real part. I'm sorry, I mean the imaginary part. If you have let's say this one has, let's compare these two. Okay, let's compare these two. Okay, what's the difference between those two? Okay, you have same real part, but you have different imaginary part, so you have different frequencies. Okay, and how about that one? It's not oscillating. Okay, but in any case, in all those three cases, what do you have? You have asymptotically stable system where the response will die down to zero. Okay, so now can you identify which one is underdamped system? Okay, so this is underdamped, this is underdamped, this is underdamped, this is underdamped. Okay, but that's this one. overdamped, and overdamped. Okay, so this one couldn't really depict the critically damped case where the S is repeated. Okay, S is here, by the way, characteristics are denoted as S instead of R. Where the S is negative A and negative A again, well, it looks like overdamped case. You can't really tell them apart. Okay, so now is there any more slides? So this is the end of 8.2, and I think it's time for me to take a break. Okay, I'll come back with section 8.3. Okay, thank you. Stop.